Let's go back here to our PowerPoint. We were talking about intermolecular forces, and we are now about to look at the properties of liquids so that we can explain the properties, some of the properties of liquids once we have dug into the intermolecular force aspects. We're going to be looking at a few of them, and here they are: surface tension, viscosity, capillary action, the formation of a meniscus, vapor pressure, and the boiling point. Now, for today, we're going to talk only about the boiling point. You all remember that we've talked about this many times. It is the temperature at which a liquid vaporizes into the gas state, right? But not only specifically that, but remember when we draw those heating curves in our first experiment, we showed how essentially during both the melting and the boiling point, the temperature levels off. It reaches kind of like a plateau because all the heat that's being put into the substance, rather than increasing its kinetic energy, is going towards specifically breaking up these intermolecular attraction forces. Now, what is interesting is that all these properties tell us a little bit about what the intermolecular force strengths are. Let's look at dipole-dipole attraction and its effect. So here are two compounds, formaldehyde and ethane. You can see the formulas there on the second column. You can see that formaldehyde has an oxygen, and of course, you remember the structure. You can see it here, two columns to the right. You can see the structure and the space filling model of formaldehyde. And then you can see the same for ethane. The reason I chose these two is because notice that they have essentially the same molar mass. Not only that, but approximately they have about the same shape. Maybe ethane's a little more elongated, but they have almost kind of like the same shapes here of the molecules. So what that means is that for these two molecules, the London dispersion force component is pretty much the same. They are going to interact with other molecules of their kind through London dispersion forces pretty much of the same level. However, what is interesting is that although both of these are low, notice that the boiling point of formaldehyde is quite higher than the boiling point of ethane. Now, what is the difference between these two molecules? Well, you can see here, if you look at the molecule of formaldehyde, that there is a dipole running through the molecule towards the oxygen. And that means that this molecule is polar. And therefore, it is capable of dipole-dipole forces. Whereas ethane, which is totally nonpolar, cannot engage in those kind of forces. So it tells you that for two compounds that have similar size molecules, the dipole-dipole force generates an extra amount of force. Now, why is the boiling point telling me that? Because remember, when I calculate the boiling point, what I'm asking is, to what temperature do I have to, raise this liquid in order to get it vaporized? Or in other words, how much energy do I have to pump in to break up, not the molecules, but the interactions between the molecules of this substance so that they can be released into the gas state? Well, the more energy required, that means the higher the temperature is gonna get before I see that vaporization happening. And therefore, as you can see, the strength of intermolecular forces can be seen through the boiling point of two substances. The boiling point becomes a useful tool to assess what strength of intermolecular forces are present between two compounds. And that's very helpful. Now, many years ago, scientists did this experiment. They took elements in the third, fourth, second, third, fourth, and fifth period, And they analyze all of the compounds that the compounds those elements make with hydrogen. Somewhat kind of like saying, well, these are the hydrides of these compounds. And they searched and they found the boiling points of each one of these. And you can see the trends here. For each period, we're plotting elements in the 4th, 5th, 6th, and 7th groups in there, right? Group 7A, 6A, 5A, and 4A. Look at the bottom line here. As you go from, let's say, a tin hydride all the way to methane, which would be the carbon, H4. So this is basically considered XH4, where X in this case is an element in the 4A group. Notice that as you decrease the atomic number of that central atom, so does the boiling point, right? You can see the trend going downwards here. And you know what? It holds true for the other ones. Look at the halogens from HI to HBr to HCl. The trend is for the boiling point to drop as the size of the central atom or the main atom becomes smaller. And it's true for all of these. In other words, the trend here is that as you decrease the molar mass of these molecules, so does the boiling point, right? Well, notice that there is an exception here for 3 of these. The boiling points of water, hydrogen fluoride, and ammonia do not follow that trend. Once you get there, you have a much, much higher boiling point. So high, in fact, that it must represent some kind of intermolecular force there that we had not reckoned with. There must be something that holds these molecules closer and tighter together and therefore requires much more energy to vaporize them than it does the other counterparts in the same groups or families. This force was studied and it received its own name. It is called a hydrogen bond. So it's a dipole-dipole interaction, but it is so strong that we have put it in a separate category. It's an attractive interaction between an unshared electron pair, a lone pair, on an electronegative O, N, or F atom, and the positively polarized hydrogen, wow, that's a mouthful. Let's say the partially positive hydrogen atom bonded to another electronegative O, N, or F. So you can see on the left there what happens in water. The partially positive hydrogen on the water molecule on the right is being drawn towards the partially negative oxygen of the water molecule on the left. And you can see it down here. We sometimes draw it in many textbooks, especially, for example, in biochem textbooks, as a dotted line between them. Notice, we call it a hydrogen bond because it is so strong. It is not a covalent bond. In other words, the water molecule is not breaking and transferring a hydrogen over to the other water molecule. No. What's happening is that the dipole-dipole force between these molecules is so strong that it just outshines, outperforms any other dipole-dipole interaction that we know. But notice that in order for it to work, the hydrogen that is partially positive has to be attached to either an oxygen, a nitrogen, or a fluorine atom. Okay, a little exclusive in there. You can see on the right the same thing between the partially negative nitrogen of one ammonia molecule and the partially positive hydrogen of a neighboring ammonia molecule. Again, we use these dots to connect them and represent them. These are very, very strong interactions, stronger than a regular dipole-dipole and stronger than London dispersion forces. And they explain why the boiling points of water, ammonia, and hydrogen fluoride did not follow that trend that we saw across their respective families or groups. So let's do an exercise here. I'm going to take us to our uh, handout here. All right, let's see if we can get this to work. And let's see if I can get this thing to work for us today. You know, I'm saying that sometimes these things are very sketchy. So this is the slide you have coming up next. And I just want us to look at it. Again, if it gets a little blurry or something, please forgive me. I'm going to try my best. So what I have here is we have 4 compounds. Let me see if I can zoom in just slightly into them. Oops. This thing never stick. All right, there we go. That's probably a little better. I know it's a little blurry anyway, but you have the slides on your notes, right? So here is on the left, we have a compound called butane. Then we have propanal, then acetone, and then propanol. I want you to look at, first of all, the fact that these are all, when you look at the electron density maps on the top, they're all pretty much the same size. In other words, as far as the one type of intermolecular force that is dependent on molecular size, the London dispersion force, they're all going to be the same for all 4 molecules. The issue we're going to ask ourselves is which types of intermolecular forces are going to be present in a sample of this substance? Well, first of all, London dispersion forces should be present in all of them, right? All of them should be able to have London dispersion forces because all molecules do. Now let's look first of all at butane. Notice that butane is made up essentially of carbon-carbon and carbon-hydrogen bonds, all of which are nonpolar. As you can see from the picture, there is no asymmetry of the distribution of electrons in those clouds. They're all pretty much the same, which means that butane is not polar, and therefore it won't be capable of dipole-dipole forces. And since there are no hydrogens attached to either oxygen, nitrogen, or fluorine, it also will be incapable of hydrogen bonding. Let's skip over to the one on the right. This is propanal. So we can see from the picture on the top, there is a distribution of electron density more towards the right side because that's where this carbon-oxygen bond is. And because that region, if you do the actual shape, you'll see that it is kind of like trigonal planar, and therefore it is going to be non-symmetric and polar. Well, that tells you that this compound is capable of dipole-dipole interactions. However, there are no hydrogens connected to oxygens here. This hydrogen is connected to the carbon, not to the oxygen. So therefore, there is no hydrogen bonding here. The next one over is acetone. And as you can see, it also shows a uneven distribution of electron density towards the top. Again, it's where that oxygen is. This carbon here has 1, 2, 3 groups of electrons around it, so it's trigonal planar, and therefore there is a net dipole pointing towards the oxygen because the molecule is not symmetric. So this molecule is also capable of dipole-dipole forces. But again, the hydrogens are not connected to an oxygen, nitrogen, or fluorine, so there is no hydrogen bonding in this molecule. Now let's look at the last one, propanol. Notice that the difference here is that in this case, you have at the very end, you have an oxygen hydrogen. You can see in the picture at the top that there is again, an uneven distribution of electron density around that side. So that means that this molecule is polar and therefore capable of dipole-dipole forces. But there's an extra feature here. And you cannot see it here because they didn't draw the structure, but this OH here that we have on the right hand side, this OH here, is actually a carbon, oxygen, hydrogen bond. I'm not going to show the rest of the carbon there. In other words, you have a hydrogen connected to an oxygen in this molecule. That means that these molecules will be able to interact through hydrogen bonding. Now, remember we said that in the grand scheme of things, and we look at it from afar, the stronger the intermolecular forces, the higher the boiling point. Notice that for butane, which is only capable of London dispersion forces, boiling point is 0. Notice that for propanol and acetone, both of which are capable of dipole-dipole forces, the boiling point is in the 50-something degree Celsius range. Much, much higher than butane. Why? Because they have the addition of these other types of forces. And then, of course, when you get to propanol, you have a boiling point of 97 degrees. Why is that much higher? It means it takes a lot more energy to pull these molecules apart from each other. I mean, they want to stay in the liquid state. You have to pump a lot of energy to cause that liquid to boil. Why? Because they are being uh, uh, brought together by the strong hydrogen bonding interaction. All right. So let's go back now to our PowerPoint once more. We're about to start wrapping this up here. All right. And let's look at the same chart that I just gave you here. Okay, so these are the 4 molecules. You have that in your handout. And again, you can see where the presence of this OH there results in a much higher boiling point because of the addition of hydrogen bonding interactions. Now, let's do an interesting comparison here. Let's spread out that compound. Let's compare with other compounds similar to itself. These compounds that have that OH, that oxygen, hydrogen group of atoms, we call them alcohols. Notice that this is not the hydroxide ion. These are not ionic compounds. These are essentially carbon-based compounds that have this group, covalently bonded, the OH. These are called the alcohols. And notice that in this table, what I've done is I've placed 5 of them. One of them is the one that's up here, the propanol, but we're calling it specifically 1-propanol. And then essentially what we're saying is that all of these compounds have that single OH group. In other words, all of them are capable of hydrogen bonding interaction. What is different is that they have progressively longer and longer carbon-carbon chains, or another way of saying it, it's bigger and bigger molecules. Over here you have the common names: methyl alcohol, sometimes called wood alcohol because you can get it from the burning of wood. Ethyl alcohol is also called ethanol. Of course, that's the one in alcoholic beverages. Propyl alcohol, you don't see that much, but you see its cousin called isopropyl alcohol. That's the rubbing alcohol we buy at the drugstore. Notice when you compare the boiling points of these 5 alcohols, remember, all of them are capable of hydrogen bonding. All of them are capable of dipole-dipole forces. However, you can see where the boiling points are progressively and progressively higher. So think for a moment. What do you think is causing the boiling point to be higher as you increase Nothing except the sizes of these molecules. That's right. The only force that is susceptible or influenced by the sizes of molecules are the London dispersion forces, just sometimes abbreviated as LDF. As the sizes of the molecules get bigger, so does the strength of the London dispersion force attraction, and that is reflected in the boiling point of these substances. All right, so let's kind of like summarize this grid of relationships between molecular sizes, polarities, intermolecular forces, okay? The type of exercise that we typically work with is when we determine which substance has a stronger total intermolecular forces, or alternatively, the higher boiling point. Typically, we're going to compare two compounds, and we're going to ask, which one do you expect to have the stronger total intermolecular forces? Which one do you expect to have the higher boiling point? Let's follow these guidelines. First, examine the substance, and you may have to draw the Lewis structure to determine if the substance is polar and if it is capable of hydrogen bonding forces. If so, it likely has the stronger intermolecular forces, and as a consequence, the higher boiling point. We saw the comparison of HF with HCl, HF having the higher boiling point because it is capable of hydrogen bonding forces. Notice that chlorine being a bigger atom, you would expect HCl to have stronger London dispersion forces, but the hydrogen bonding kind of like takes over here. The second scenario is when you're comparing two molecules of very different molar mass, regardless of whether they're polar or not, the London dispersion forces component is more important. So you compare HBr with HCl. You know, the HCl bond should be more polar than the HBr bond. So HCl should have maybe stronger dipole-dipole forces. However, HBr has the higher boiling point, which indicates that it must have stronger intermolecular attraction forces. And since the only difference between these two is the London dispersion forces, that must be due to the bigger size of the bromine atom. All right. Now, if you're comparing two molecules that have pretty similar molar masses, in that case, dipole-dipole forces are going to be more important. And we can predict that the substance that is polar will have the greater intermolecular forces, i.e. the higher boiling point. So compare carbon monoxide with nitrogen gas. If you draw the Lewis structures for them, you'll see that CO is polar. They're both about the same size, about 28 grams per mole. And yet you expect carbon monoxide to have the stronger intermolecular forces. Of course, from a certain perspective, to say stronger intermolecular forces is kind of relative, right? Because both of these are gases, both of them have very weak intermolecular forces. So the difference between them is, minute and probably not something we would observe under normal conditions. We would have to go to somewhat extreme conditions in a lab to determine the difference between them. Okay, let's close out here. I added a couple of exercises here for you, and I'm going to post them here quickly. I want you to think a little bit. This is not in your slideshow, by the way, so you might want to kind of write it out. So again, let's ask what types of intermolecular forces are present in the following compounds. Like I said, you may have to draw out the structures because sometimes the way the formula is written might mislead you a little bit. Don't forget, hydrogens are never at the center of a molecule. They never form a bridge between two other atoms. They are always on the periphery, always on the outside. So remember, we have three choices. We have London dispersion forces, we have dipole-dipole forces, and we have hydrogen bonding forces. Right? So let's see. What do you think for CO2, carbon dioxide? Which of the three? That's right. London dispersion force only, right? Okay, CCl4. Well, the carbon-chlorine bond is polar. But the second question is, are those polar bonds distributed symmetrically or not symmetrically? And I gave you a little shortcut that you can do when doing these structures in our Vesper practice sheet. I walked you through a video where I told you what the shortcut is, right? You ask, is everything on the central atom the same all around? And since this molecule is symmetric, it is nonpolar. Therefore, it can only do LDF. Next one, CHCl3. It looks like the second one we replaced one chlorine, substituted hydrogen in for it. So what do you think now? Yeah, it might help to draw it actually, you know. Let's see if I can get this pen to work here. Right. So you have, let's say your H there. And let's say you have chlorine this way. Another chlorine here. And then a chlorine kind of back there. Right. And of course, if you want, you can put all the lone pairs on the chlorines. So notice that in this case, the carbon-hydrogen bond is not polar. But all of these guys are essentially pointing towards the chlorine atom, which is more electronegative. And since in a tetrahedral structure, all of those are on the same side, that means that this molecule has now become non-symmetric. Therefore, polar, right? So that means that CHCl3 should experience dipole-dipole forces. But remember, it also experiences London dispersion forces because everybody does. All right, let's work here with our piece Cl3. Erase all this here. Made a mess here on this screen. All right. I'll let you guys do the PCl3 and just let you know that this one also will experience LDF and dipole-dipole force. I was going to say double dare because my kids used to watch that show on Nickelodeon long time ago in a galaxy far away. Okay, last one. We already saw this one, right? CH3OH. It belongs to that sequence that I showed you of the so-called alcohols. If you draw the structure properly, you'll see there's an OH in there. So in other words, there's three hydrogens attached to the carbon, one attached to the oxygen that allows this compound to participate in hydrogen bonding. So we're gonna have all three forces in there. Cool. Okay, when we break off here, you can let me know how you did on that one. Let me ask you one more question just to think about. Maybe I'll let you take this one home. Explain why ethyl alcohol, that's the formula over there, has a higher boiling point than methyl alcohol. And that's the formula there. So the boiling point of ethyl alcohol is a good, 14, almost 14 degrees higher than methyl alcohol. But what's the difference between them? That's right. They have different sizes, right? The ethyl alcohol is a bigger molecule, And what is a type of force that is susceptible to the sizes and shapes also of molecules? Right. So ethyl alcohol has a larger molar mass or size. I should probably say molecular size. So it has stronger London dispersion forces than methyl alcohol. And that makes it harder to pull apart the molecules of ethyl alcohol to convert the liquid into a gas. Okay, we are going to stop here. So let me ask if anybody has any questions. Let me come back over here. Hey, let me show my face again. I'm sorry about that. Let me know if anybody has any other questions. You can either unmute your microphone and ask or put it on the chat room. Somebody's asking Hulk length, shorter bond length equals stronger bond. I assume that's a question. I'm gonna ask you here. So let's say yes. Does anybody have any questions?
Professor, could you show the very last slide again? I just had to write down the answer.
Oh, sure, sure.
Thank you.
No, no problem. Here it goes. Sorry, wait until I think there's some floating menus that seem to get in the way here. Okay, there we go.